So if we calculate this, we find minus 143 watts per meter or minus 1.4 watts per centimeter. Why minus? Because it's in the minus R hat direction. The heat is flowing inward. Okay, let's move on to part B. Estimate roughly to what value in millimeters of mercury the pressure of the gas between the walls must be reduced before the heat influx due to conduction is reduced below the value calculated in part A by a factor of 10. Okay, so let's look at the thermal conductivity of helium with the new number density, because we are reducing the number of gas molecules. It is 1 over 3 n prime c v bar 3 kt over m square root multiplied by L. Now actually here for the temperature of the helium gas, we should pick something in between 0 and 25 degrees, because this is basically temperature is decreasing as we go inside. So normally you could take this T value to be 12.5 degrees Celsius, let's say, but this is going to give you a numerical error that is not very significant. Remember that this theory is valid for not very high temperature differences. So taking it to be the room temperature is not a bad approximation in this case. So we're considering room temperature KT value. And this is now going to be in vacuum conditions. So in vacuum conditions, we replace the total scattering cross-section, the mean free path, with the boundaries of the box, delta R, and such that the thermal conductivity kappa becomes pressure dependent. So it depends on the pressure. Normally it's not dependent on the pressure or N, but because we have the vacuum situation here, the mean free path becomes pressure dependent. So with this new thermal conductivity, 0.053 kappa prime is 0.053 divided by 10, because we have a factor of 10 reduction in thermal conductivity here. A factor of 10 reduction in heat influx, that will be due to a reduction in thermal conductivity, because del T del R is not changing. So del T del R is constant. What is changing is the thermal conductivity. Okay, so 0.053 divided by 10, our new thermal conductivity value will be equal to 1 over 3. Now, at the same time, we have the ideal gas law. P bar is n prime kT. So we can use for n prime P bar divided by kT. That's due to the equation of state, ideal gas law. Then we have C square root 3 kT over m for the mean speed of the molecules. And for L, we have a constant value, which is delta R. Now this gives us P bar C delta R 1 over square root 3 mk T. All right. So k squared t squared will cancel. So we will be left with square root kt at the bottom, and this will be going inside as 9. So we will obtain square root 3 here as well. So what will be this pressure, P bar? It will be the new thermal conductivity, square root 3 mkt, square root 3 mkt, divided by C delta R. And we have kappa divided by 10, our new thermal conductivity. We have C 3 over 2k, 2 over 3k, 1 over C. And then we have square root 3 mkt square root 3 mkt divided by delta R. And this will be the original thermal conductivity divided by 15K, 15 times Boltzmann constant, square root 3 mkt, 3 mkt square root divided by delta R. Now this is basically our answer. We can calculate what value this corresponds to. The p bar value is 0.053 divided by Boltzmann constant times 15, 15 times 1.38 times 10 to minus 23, and then we have square root 3 mkt, so we have 3 times 4 10 to minus 3 kilograms divided by Avogadro's number, 6.02 10 to 23. Then we have kT value 1 over 40 electron volts at room temperature, 1 over 40, 1.6 10 to minus 19 coulombs, square root, divided by delta R. Delta R here is 5.3 minus 5, 0.3 centimeters. That is 0.3 10 to minus 2. So here I'm approximating kT helium to be KTR. Okay, so this is what I'm doing. Or we could use T helium to be 12.5 degrees Celsius. That would be a good approximation as well. Okay, so with that, we obtain the mean pressure P bar to be 0.762 pascals. That corresponds to 7.5 times 10 to minus 6 atmosphere, and that is approximately 5.7 times 10 to minus 3 millimeters mercury. Here, 1 atmosphere is 1.01 10 to 5 pascals, and that is equal to 760 millimeter mercury. So that's the conversion we're using. And our final answer here is roughly 5.7 10 to minus 3 millimeter mercury. Okay, so in this problem, we considered the degree of vacuum necessary to achieve thermal insulation. In part A, we calculated the heat influx, which is minus the thermal conductivity of helium that fills the space between the outer surface and inner surface of this dewar, multiplied by del T del R gives us the thermal conductivity multiplied by temperature gradient gives us the heat influx. And for that, we need to know the thermal conductivity of helium. We have used the law of thermal conduction, the elementary kinetic theory that gives us 1 over 3 and V bar CL. Here is the N is the number per volume, V bar is the mean speed per molecule, which is approximately equal to the RMS speed, square root 3 kT over m. C is the heat capacity per molecule, which is the derivative of the mean energy per molecule with respect to temperature, which is 3 over 2 kT according to equipartition theorem for a monatomic gas. So C is 3 over 2K, and the mean free path is 1 over square root 2 n sigma, which has the total scattering cross section 4 pi r square in it, where r is the radius of helium. So this r is the radius of the helium atom, which we can estimate to be 10 to minus 8 centimeters. That gives us sigma. So substituting all of these values here, and for mass of helium, the atomic weight 4 times 10 to minus 3 kilograms divided by Avogadro's number, and for K we use this value, we obtain thermal conductivity of 0.053 watts per meter Kelvin. Now P divided by 2 pi RL power, heat per time per area. Now the area, cross-section area that this heat influx sees is 2 pi r times L, the length of this cylinder. So this gives us P over L is minus 2 pi r kappa del T del R. If I isolate temperature and R here and integrate from outside to inside, I obtain a power per area of minus 1.4 watts per centimeter. So that was the question. The heat influx in watts per centimeter height of the dewar due to heat conduction. And under vacuum conditions, when the thermal conductivity of helium is reduced by a factor of 10, this heat influx will be reduced by a factor of 10. So with that, the new thermal conductivity, because this is a vacuum condition, we are estimating L to be equal to the dimensions of the box, which is delta R here. Therefore, this n prime, which is P bar over KT, actually affects the thermal conductivity because L has saturated in the value of delta R. And by substituting these quantities here, we obtain a P bar of kappa over 15K squared 3K mkt over delta R, which has a numerical value of 5.7 10 to minus 3 millimeters mercury.